Good morning, everyone. We're about to get started, so if everyone would take their seats, that'd be great. So I have a couple of small announcements this morning. First of all, a few people asked me how they can find out more about the robots that were at the reception last night. So I have a few of the cards from the people who ran that, and you can find those on the table at the back next to the name tags. You can also find them at bot, as in robot, bot-party.com. My other announcement is that we have a late-breaking addition to the program. For people who are interested in a deep technical talk, Joe Stringer will be giving a talk titled "Revala What? Keeping the Flow Cache Fresh." At the tail end of lunch from 12:30 to 1 o'clock in here. So anybody who wants to find out about how vSwitch keeps flows in the data path correct as the flow table changes, will want to tune in for that. And now for our first talk of the day, we have Vikram Dham from Kamboi Technologies, who will be talking to us about MPLS using OpenFlow.
Thanks a lot, Ben. Good morning, everyone. So my topic is trying to implement part of MPLS using OpenFlow. This is the work which it has been done in some form in past by some of the companies internally for their own consumption. And I got this project as part of a customer requirement. So I would like to share my learnings and experience in this. To give you a background about myself, I'm a CTO of a small company, Kamboi Technologies. We work with switch vendors, some companies which are early adopters of SDN, looking at proof of concepts, and even looking at some product ideas in traffic engineering currently. In past, my background is not from networking like CCIEs or something, but I've come from network application development from a company, Sling Media, where I built the P2P software for connecting like Sling boxes, devices. You can imagine like we were doing UDP tunnels using hole punching and stuff in the years like 2007 and 2008. So that is a background. And when I see like things like VXLAN and stuff, it just looks to me like taking tunnels and pushing a stack down to the kernel. So that's my background. So as I mentioned, some things about this project. This came as an exploration request from one of the customers. They heard about the stories about a very big data center of Google who were using MPLS internally, and they wanted to explore like what is feasible, what they can do, and this is one of the parts of the project. Okay, it's all built using open source components. I would say 90% of the code already existed. It just need to be glued together. OVS, and some other components which I'll go in detail in the next slides. Before I go further, how many of you guys here know about route flow and they have used route flow? Can I see a show of hands? 2, 3, 4. Okay. Okay. Out of 60 people, 4 people. Okay. How many people know Linux containers are very hot? Okay. More people. So yeah. So I'm a big fan of route flow. I have worked with route flow. I can say in one line, it's a very nice piece of work. And they have been using Linux containers for more than past 4 or 5 years already. And I'll go into the detail in the next slide is architecture, right? So what we have done here is, right, MPLS, right, there are two main different domains, right, how you can do MPLS. One is the legacy things, protocols like LDP, BGP, where peer-to-peer nodes talk to each other, and they can exchange the labels, and they can come to an agreement what the labels are for the traffics. Second approach, which is very popular in SDN world, is like you use a centralized controller. It knows the topology of the network, and it can push down the labels. Both have their strengths, right? Legacy world, you need to talk. You cannot live without that. Centralized is more intelligence. You can make faster, more intelligent decisions. The best approach is putting them hybrid together, right? Like on the edge, you would need some form of protocol to talk to legacy network somewhere. Your customers would have BGP or LDP. And centralized allows you for your autonomous system to take the intelligence and make intelligent decisions, right? So that way, I think SDN is very good, but the transition path lies currently, at least for next few years, is even to be able to talk to legacy protocols, peer-to-peer protocols, distributed protocols, which are not just controlled by one central controller. That is where comes in route flow. What route flow has done is, right, it has provided a very nice path for people looking to migrate from legacy networks to controller-based networks. As a first step, right, you need to be able to talk, to talk to your legacy protocols like BGP, LDP, RIP, OSPF, whatever is already in your network. I can't go to the IT guy and say, hey guys, rip it off, I'm getting my OpenFlow controller, let's get started. No. So the approach, what these guys have taken is, they have taken open source routing software Quagga, which has so much of effort already in the community, and they have glued it and interfaced it with OpenFlow protocol, okay? So imagine the power of this thing, right? You have open source Quagga routing software, which has been built by open source community for so many years. It is in production in so many places, very big networks, and now suddenly you can use that information and program your OpenFlow switches, be it commodity switches like PK8s, switches, chips coming from Broadcom, whatnot. You can get the line rate, or you can even run it in your virtual instances, already like Vata is doing. So this allows us to run it with commodity switches in hardware, and you can get better performance in terms of speed. So that's what RouteFlow does is, what it does is it takes your Quagga instances, listens to the information coming on netlink for the host and the route updates, and converts them into corresponding OpenFlow mods and pushes them to the OpenFlow switches, which is very powerful, as I mentioned. And the way they do it, right, they are basically three-tier architecture they have. The topmost layer is, so what happens is for each of the switches, right, switches itself, OpenFlow switches, they don't have any routing information. For each of the switch, which you want to convert into a router, they run a Linux container which has Quagga running inside it in a server, okay? And the NICs of the switch, the NICs of the Quagga instance, which is running in a Linux container, they're mapped to the ports of the data path ID of the virtual switch, or the, in case like PK8 switch or an OpenFlow switch. So whatever happens is, initial flow mods are there, whatever routing control information is coming like BGP, LDP, OSPF, that goes to the Quagga instances running in Linux containers. Quagga doesn't know that it is running in a virtual instance. It just thinks, oh, it got a control packet from a particular NIC, it does its magic, it calculates routes, it discovers its neighbors, and pushes that information down using netlink. And this is where RouteFlow comes in, and it listens that information on the netlink, and it pushes down to the RF proxy layer, which is running on top of the OpenFlow controller, and converts those route information, neighbor information into corresponding what it should be the flow mods. So this is what all the magic and the glue RouteFlow guys have done. Very nice project. Can't say enough words about Linux containers and networking looking at RouteFlow. So that was the background, right? And when I started working on this in the open source, mostly they had components for IP routing, RIP, OSPF, BGP. And as I said, request was for looking into MPLS. And one part of MPLS we were looking was LDP. LDP allows this peer-to-peer exchange of labels. How many are comfortable with MPLS here? So I don't know if I need to go with the slide. Okay, so I'll just cover a couple of minutes here. So MPLS, advantages of MPLS I'll start with so that people are motivated to look into it. Two main advantages. Number one, faster switching compared to IP routing. MPLS allows people to add prefix labels before IP, between L2 and L3 layer. So because of that label, which are integers, the switching fabric doesn't have to do a prefix match on the networking bytes. Instead, it can do an int match, which is much faster for the, especially in the core. That's where people prefer MPLS in the core. And secondly, you can install paths across end-to-end using your own labels. Okay, this is something where you can use centralized and stuff. And you can do your custom paths, tunneling, multipathing, all the cool stuff, right? So this is basically what the advantages of MPLS are, what is the driving factor, right? In a data center or on the WAN, right? If you look, you want to do multipathing, you want to do tunneling, right? You want to do traffic engineering, MPLS would be one of your choices. So on the implementation side, what MPLS is, right? So I discussed, right, LDP is the protocol. There's a daemon corresponding in Quagga, LDPD. What it does is, the the neighbors talk to each other using LDP protocol. And they need to figure out what the labels are for each of the IP traffic they can send to each other. They talk to each other, they exchange those labels, and they push basically two kinds of information to the net, to the OpenFlow. One is called as NHLFE, which is next hop label forwarding entry. And what that does is it tells, basically in a very plain words, it tells OpenFlow switch, hey, if you have an incoming packet on a particular port for an IP destination network this, what are you going to do with that? Push a MPLS label. That is FTN actually, sorry. So you put an MPLS label, push the MPLS label to that and send it to a particular port. NHLFE, what does it? It only looks at MPLS packets. If incoming label is post 5, what do you do with that? Incoming label is 7, what do you do with that? So it looks at the MPLS label, then it has a table there, it knows what it has to do with a particular label. So these two things are of interest to us, NHLFE and FTN, and this is what we pick from Quagga's open source code, and we send it to the route flow. So now I'll discuss the few of the implementation changes we made, right, to support this. On the top, as I mentioned, Quagga is sending NHLFE and FTN. Initially, it was doing netlink, but then we changed it to use forwarding plane manager. Forwarding plane manager is Quagga's way of talking in user space using sockets instead of relying on netlink. So you can imagine with this, your Quagga instance could be at one place and your RF client could be at another place. RF client is the code which is responsible for listening to the netlink or the FPM messages. And it listens to these messages and then it sends it to something called as RF server. RF server, it has a mapping of, because Quagga instances are virtual, they are running our nice Linux containers. They need to be mapped to the physical ports of OpenFlow, which have data path ID and port. So RF server has that information about mapping between Quagga virtual instances and the real physical ports and the data path ID and port. So it does that mapping and it constructs a new packet and it sends it to the RF proxy. Okay? RF proxy is what is sitting on top of the OpenFlow controller. It takes this, it pushes these flow mods to the OpenFlow switches. Imagine any hardware OpenFlow switches. In our case, we are using OpenFlow 1.2. And also it listens for incoming packets from the physical switches, which I discussed earlier, like control information, BGP, LDP. Those are packeting events, and those are what it sends upwards to our Quagga. So this is basically what all we did, right, in terms of the code changes and the architecture changes. And I said, right, in the last point, you see a lot of code is from open source. Quagga was already there. LDP implementation was also done. We did not have to make, in fact, any change in the LDP code. Only change we had to do is, like, in order to use forwarding plane manager, and on the Quagga's lowest layer, which interfaces with the kernel and FPM, we had to insert code so that we can listen to MPLS information coming from LDP protocol and convert it into FPM messages. And another change what we had to do is, on the OpenFlow switch, we had to implement these entries, right? I mentioned LDP control information are two types. One is initially when the switches turn on, they talk UDP, hello package to their neighbors. Hey guys, I'm present. So those packets we are forwarding to the RF proxy, to the route flow actually. And second part is the TCP packets, right? Which is the keep live session, persistent connections maintained between neighbors for exchange of the MPLS LDP label mapping. And that's TCP also connection we take from the OpenFlow switches and we terminate in our route flow instance. Okay. Anyone has any questions yet, or you can take it in there? Okay. So this is the background, right? What route flow is, what changes we did, MPLS LDP. Next, I'll go on to a small demo. We are not taking a chance with Murphy's Law, so I did a video recording of the demo, okay? I was really tempted, but I don't want to take a chance in the time constraint. So I'll show you the demo test bed. This is a demo test bed. So what it is, right, the topology is on the top left. What we are emulating here is using a mininet virtual machine. So they are in the test, this was run on a virtual box, okay? We are running two VMs main. One is the mininet VM, okay? And second is this route flow VM, which has the 4 Linux containers we discussed, right? Each of the 4 Linux containers correspond to the 4 routers you see in the top left picture. Mininet VM has 4 switches, A, B, C, D, okay? Their controller, they're talking to the RF proxy in the Routeflow VM. If there are any BGP, this network is configured for OSPF topology. If there are any OSPF, LDP, or ICMP packets, they all go to the RF proxy. RF proxy does the lookup, maps to the right Linux container, be it router A, router B, C, or D. All of them are running their respective Quagga instances. And the Quagga, as I mentioned, is a custom Quagga with LDP changes, FPM enabled, and that is what is running in the Routeflow VM. I'll start the video now, and we'll see. Okay, so this is what I mentioned earlier, right? We have these 2 VMs, okay? One is on the left is the Mininet VM, which emulates our topology. On the right is the Routeflow VM, which is running all the 4 Linux containers. So move it a little forward. So we're going to start some XTerms here so we can look at the things. So right now what we just did is we started the Mininet topology. All the hosts have come, okay, all the switches have come up. So this is the topology which I was showing, right? So all the hosts, H1, H2, H3 have come up. A, B, C, D, the routers have, the switches have come up. They are still not routers. They'll become routers when we turn on our Routeflow software now. So now we go to the Routeflow VM, which is basically on the right side, okay? And this is where we started the Routeflow software on the right side VM you see. So what it is doing initially is doing mapping, is building a map, okay? What the physical ports are, what physical data path IDs are, and it is talking to the Quagga in the Linux containers and understanding what their VM IDs are, what their ports are. It's building a map, and then it has already done its job of, creating the OSPF routes, LDP routes, and it has pushed them to the OpenFlow switch in the Mininet. So now we are on the Mininet VM, and we'll try to see the flow table for one of the switches which it got from the Routeflow. So can you guys see it like it's not readable, or it's readable? No? Okay, let me see if I... Okay, so we'll go cover this in one of the later slides actually. So basically to give you an idea, right, this is showing the flow tables for one of the switches. We use multiple tables in this context. We have table 0, table 1, and 2. Table 0 looks at incoming packet is MPLS, go to table 1. Incoming packet is not MPLS, go to table 2. Table 2 is all the default IP routing, all the other things I discussed. Table 1 is what holds all the NHLFEs, MPLS, packet swaps, POPs, those happen in table 1. So that's why we are using multiple tables here. So now I have gone back into the instance for the Routeflow, and here I'm showing, right, I have listed what are the different containers which are running in this. For each of the routers, there is one container, as I mentioned. Now we are trying to go inside one of the containers, which is RFVMA for the router A in this case, okay? So we log into that container and we look into the routing information and the MPLS information inside that container. So this is inside that router, right? What all routes it can see, what it has learned from OSPF. These are the interfaces, what it has on the container, which map to the topology here. And now we are inside the VTY interface for Quagga, and you can see inside this, right, we can run these MPLS commands. Here I'm doing, first I'm going to do is MPLS LDP discovery. So this node can see its neighbors here. So next we are looking into what the neighbors are for this particular node which it has learned. And lastly, we'll look at the MPLS label bindings, what it has learned from its neighbors. Okay. So as a final test, right, what we'll do in this is, right, to understand the flow tables, we ran a test of iperf between H2 and H3. What this did is it basically exercised the network so that routers B and C act like label edge routers, router A acts like a label switching router. So after the iperf, actually we are running short of time, but if after the iperf you can see the packet counters incremented for the corresponding MPLS entries. So this is basically the demo I want to share, and this you can build today using the code. And I'll go back to the slides. This was the demo. So some of the highlights from the presentation, we have sample wire capture here. So this is the packets I discussed, hello, and the label mapping, which are being exchanged. This is the MPLS packet capture on Mininet, MPLS packets going back and forth as part of the iperf test. This is the routing multiple tables, what I discussed, table 0, 1, 2, pop, push, swap actions. Important takeaway from one of this is like LSR, we can combine tables 0, 1, and 2 for LSR. Okay, but for LER, label edge router, it gets a little tricky because after we do a pop the label, we need to send it to the IP table for finding the correct output port and routing the packet. So for LER, we need to use multiple tables, and that's where we may not be limited to cheaper commodity OpenFlow switches, but one option would be to use costlier FPGAs and NPU-based switches, or another option would be to just terminate LERs on the hypervisor like the software switch. So the takeaways, finally, it's line with what Guido was mentioning yesterday. I was listening, right? Keep as much intelligence as possible outside the core in your edge, okay? Make your core as dumb as possible. And secondly, right, keep the code which is interfacing with OpenFlow controllers, make it very lightweight. Don't be dependent on it's a X controller, Y controller, Z controller. You should just be interested in events like packet ins, packet outs, flow mods, that's it. And that you can do with C, Python, Java, but keep it very lightweight for you to port it. And remember, software OpenFlow switches are not equal to hardware OpenFlow switches. When you're working with a hardware vendor, make sure you understand what they really support and what they don't support. That's very critical. And one of the challenges we saw when doing this project is when you're dealing with multiple tables and different protocols, it is pretty challenging to merge the flow mods coming from different layers. So perhaps we need some software tools or some libraries to make that easier for the developers. And OpenFlow and OpenVSwitch no doubt is great. It helps avoid vendor lock-in. A lot of people are already taking advantage of it. You can pick any 2 out of the 3, speed, functionality, or cost. That's something, right? You can't get all the 3 as of today. So if you need all the functionality of OpenFlow protocol, you might need to go for costlier switches. And finally, this is a URL for the code. If you want to check it out, say you know Linux containers, networking, SDN, there's no better project than Routeflow, what I have seen yet. Check out this code. There's one build command. It should set up your Quagga instances and everything, and you should have MPLS running on your laptop. You can use it to deploy in your network, customize it for traffic engineering, or use it for tutorial education purposes. I will end it with the thanks. Any questions?
First, what controller did you use for this?
Rio.
Okay.
Yeah.
You made a comment that this is you might not be able to do this with hardware devices. These are all just standard networking IP and MPLS functionality that pretty much all the routers switches do now. So I think it should be possible.
Non-OpenFlow or OpenFlow switches?
They do. So the hardware does these functions now. It's just a matter of mapping the OpenFlow to set up the right tables in the switches, I think.
Yes, you are correct. They do, the MPLS sections are done, but it gets a little trickier with the multiple tables. So multiple tables, pipelining, it is there in some switches of OpenFlow, but they're very costly. Then the CapEx advantage, what people think, right, when they go into project, like comparing with dinosaurs, right, they think that CapEx advantage is not there. But if you want to go with like commodity switches, Broadcom still doesn't have easy route for multiple tables. They're working on it, but still not there. vSwitch has multiple tables, other software switches support multiple tables, but that's what our observation was.
This is Roxana from One Convergence. Can you put the first slide, which had the Quagga, the Routeflow architecture? I actually have a clarification on that slide.
This one? Is this?
Yes, that one. So the first block, the virtual routers, this thing, I mean, can you explain what exactly is the interfacing and relationship between the NICs in the container and the vSwitch module, Dham?
Oh, on the vSwitch module there?
Yeah, and the NICs, which are in those containers.
Yeah, that's a good question. I did not get into those details. What is happening is, I showed you one VM, which is the Routeflow VM.
Okay.
It is running 4 Quagga instances, 4 Linux containers. Some of them have 4 ports, some have 3 ports, some have 4 ports, depending on where they are located in the topology I showed. So these 4 ports, right, there is a local vSwitch running in the Routeflow VM, inside the VM.
Okay.
Okay, so these ports from virtual, it's coming from the Linux containers, they're terminating on that vSwitch.
Okay.
So this is not the main switch, which is the hardware switch. This is the virtual switch running in the
Oh,
VM.
I see, okay.
Yeah, that's a good question.
Let's thank our speaker.